Hey everyone, I hope you're doing well today. In this video, let's go ahead and simplify the process of factoring polynomials completely. While I know sometimes it's a bit tricky to know when you're actually done factoring, just know that when you've written your polynomial as a product of unfactorable polynomials with integer coefficients, then you're done. And if what I just said was confusing, keep on watching this video so we can go through some examples together to clear it up. So to factor polynomials completely, let's go over a few different tools and strategies that you can use to help you do so. First, you should always try to factor out the GCF of all the terms if you see one. Second, if you can factor by grouping, this is also pretty useful. I'll go over some of these examples in a little bit. Third, noticing the pattern of perfect square trinomials will help you factor things a little bit quicker. Fourth, identifying the pattern of difference of squares will also help you factor quadratics a little bit quicker. When you see a sum of cubes, know that you can factor it just like this. If you notice the pattern of difference of cubes, you can factor it just like this. While there are definitely more details and strategies that we can use, knowing these 6 are a great start to help you factor polynomials completely. Keeping these 6 patterns and strategies in mind, let's go ahead and grab some paper, something to write with, and let's do some math together. For example 1, let's go ahead and factor x cubed plus 2x minus 15x completely. So first notice that all 3 of these terms have an x, so that's their GCF. I'm going to factor that out. And we're going to be left with x squared plus 2x, and then minus 15. Now that we have a linear term on the outside, or x, that can't be factored anymore. However, on the inside we have this x squared plus 2x minus 15, and that's a quadratic, so that might be factorable. So let's see, we know that x times x is going to be x squared, and for negative 15 we need 2 factors, but they have to add to get to positive 2, so let's try maybe negative 3 and positive 5. And if we match these up, that's going to be negative 3x, that's going to be positive 5x, and those add to get to positive 2x. Okay, so we have this x along the outside, and we should be able to set up 2 binomials here. One is going to be x minus 3, and the other binomial is going to be x plus 5. All right, so at this point, when we have all linear binomials or terms, we can't do anything more. So just keep in mind that this can't be factored, this can't be factored, and this can't be factored. This right here is the fully factored version of our original polynomial. Let's try another one. For example 2, we have 2y to the 5th power minus 18y to the 3rd power. So looking for a GCF first, I notice that they both have 2 as a common factor, and they both have y to the 3rd power as a common factor. Factoring that out from both terms, we'll be left with y to the 2nd power minus 9. All right, so what we just factored out, this 2y to the 3rd power, that's the GCF, and that can't be factored anymore. However, on the inside of this parentheses, this is a quadratic, so we might be able to factor this into 2 binomials. And so if we take a look, this is our difference of squares pattern, right? We have a difference of perfect squares, so that means we can factor that. So out in front, we still have this 2y to the 3rd power, but inside the parentheses, this y squared minus 9 is going to factor into y plus 3, or the square roots of each of them, multiplied by the binomial y minus 3. So again, whenever you have difference of squares, that's always going to be the pattern. All right, so this is our first term that can't be factored. This one can't be factored because it's linear, and this one can't be factored. This right here would be the fully factored form of this polynomial. For a third example, let's try 4c to the 4th power minus 16c to the 3rd power plus 16c to the 2nd power. Looking at all 3 of these terms, notice that they all have a 4 as a common factor, and they all have 2 c's inside of their terms as well. So factoring out 4c to the 2nd power, we're going to be left with c squared minus 4c plus 4. So when we have this monomial out in front, that can't be factored anymore, but on the inside we have a quadratic, and this one hopefully looks familiar. So think about which pattern this might be. You can look at the list of all the patterns that we have above, but this is actually a perfect square trinomial. Okay, so perfect square trinomials can always be factored into 2 binomials that are identical. So we have 4c squared on the outside, and on the inside we can write c minus 2 multiplied by another c minus 2. Okay, so this is that perfect square trinomial pattern. And if you wanted to, you can even shorten this up a little bit and write 4c squared multiplied by the quantity of c minus 2 squared. This is the same thing, just written a little bit more condensed. This monomial can't be factored anymore, and this is a linear binomial, and it can't be factored either. This right here is fully factored. So now that we've tried a few examples together, maybe let's throw in some cubes, some difference and sum of cubes as well. For example 4, we have x cubed plus 64. So this one specifically is going to be a pattern of sum of cubes, but if you're not seeing that, maybe I can rewrite it in a different way so you can see literally the sum of cubes. So we have x cubed plus this 4 cubed. 4 cubed is equal to 64. So this fits our pattern of our sum of cubes, and let's see how we're going to factor that. So now that we know that this is a sum of cubes pattern, let's go ahead and see if we can write the factored version of this. So whenever we have a sum of cubes, you write the cube root of the first term plus the cube root of the second term. And what we're going to do is we're going to multiply this by the square of the first one, which is going to be x squared. And we're going to subtract the product of the two. So x times 4 is going to be minus 4x. And then we're going to square the second term, which is going to be plus 16. So this binomial out in front is linear and it's not factorable. And what we have inside here is also not factorable. You can check the discriminant if you'd like to for that b squared minus 4ac, but I promise it's not factorable. So again, noticing our sum of cubes pattern, this would be the fully factored version of this. Let's try another. For example 5, let's try factoring 16m to the 5th power minus 250m to the 2nd power. So looking for a GCF first, as I always like to do, I notice that they're both even numbers, so 2 is a common factor, and they both have 2m, so I'm going to factor that out as well. That should be the GCF, and we'll be left with 8m to the 3rd power, which is a perfect cube, interesting, minus 125, and I think that's it, because we took out both of the m's, and that's also a perfect cube. So again, this 2m squared in front is a monomial that can't be factored, but inside here, this is going to be our difference of cubes patterns. Let me show you how we can rewrite that to see it a little bit more clearly. So we have 2m squared out in front. Maybe I'll use brackets here to show this, but the cube root of 8 is going to be 2, and the cube root of m cubed is going to be m. So you can see that this was a perfect cube because it's 2m to the 3rd power. And then instead of writing 125, the cube root of that is going to be 5. So 5 cubed equals 125. So right here, hopefully you can see that this is going to be a difference of these cubes. So let's go ahead and factor this. Well, first, let's take this 2m to the 2nd power, and let's just copy that in front. And if you need to pause the video to take a look at the patterns of difference of cubes, go ahead and do so. But the first thing we do is take the cube root of the first term, which is 2m, and write minus 5. That's the difference of those two cube roots. And what else do we have here? Then we're going to square the first term. So if we square the 2m, that's going to end up being here 4m squared. Go ahead and write that, 4m to the 2nd power. Next, we're going to add the product of the two. So we're going to go ahead and multiply the 2m by 5, and that's going to be 10m. And then finally, we're going to square the second term. So squaring 5, that'll be 25. All right, so that right there would be our fully factored version of this. Notice here we have a monomial out in front that can't be factored. We have a linear term here, a linear binomial, that also can't be factored. And when we have these sum or difference of cubes, what we have left here, even though we have a trinomial that you might want to factor, you can go ahead and try to factor it, but you won't be able to. So it's not factorable. So this right here would be the fully factored version of this polynomial. So now that we've tried a couple with sum and difference of cubes, let's bring in some factoring by grouping. For example 6, let's factor x cubed minus 3x squared minus 16x plus 48. Typically, when we have a 3rd degree polynomial or a cubic polynomial and there are 4 terms, I like to see if we can factor by grouping before doing anything else. I can't factor out a GCF, so I usually go into this strategy next. And what we do here is we basically are trying to group the first 2 terms together somehow and to group the second 2 terms. So if we were to group them into the first 2 and the second 2, this isn't going to change the problem at all. This is going to be x cubed minus this 3x squared. That's just going to be the first grouping that we have here. Now, as for the second grouping, we're going to put this minus right over here. And inside this grouping, we're going to have the 16x as we just had originally. But the only strange thing you might find is we're going to write minus 48 instead of plus 48. And let me tell you why we're going to do this, right? So again, we had this minus over in the original problem. And if you distribute this minus, then it's still going to be a negative 16x. But because we had this plus over here, keep in mind that when we did the grouping, we actually had to put this minus right over here, because if we distribute this negative to it, then a negative times a negative is going to be a positive. So keep in mind that when you factor by grouping, you might have to flip a sign to make sure it is the same problem that we started with. Now that we have 2 groupings, let's see if we can find some GCFs of each grouping. So in the first grouping, I'm looking right over here. I'm noticing that they both have x to the 2nd power. So I'm going to factor out x squared. And what are we left with if we factor out x squared? I think we're going to have x and then minus 3 left inside the parentheses. And then for the second grouping, I think if we are looking inside here, they both have 16 as a common factor. So we can write minus 16 along the outside. And on the inside, we'll be left with x minus 3. So there's the GCF being factored out of both of those groupings. At this point, we should be pretty happy because if you notice, this x minus 3 and x minus 3 are common between these two terms. And when I say two terms, what I'm really referring to is this whole thing is really one term because it's all multiplied together, and this is a second term. So again, x minus 3 is a common term for both of these, so we're going to factor that out as the GCF of those two terms. I know it's a little weird, but the GCF of them is x minus 3, so it's a binomial that's the GCF. However, what's left over if you factor out x minus 3 from both is you're going to be left with this x squared and the minus 16. Again, once we factored out the x minus 3 from both of those terms, we were left with this x squared and this minus 16, so that's where this x squared minus 16 is coming from. Okay? Now at this point, this x squared minus 16 looks like it is factorable, it is a quadratic, and so pause if you need to think about which pattern this might be, but this should be our difference of squares. Okay, so if we notice that this is a difference of squares, we're going to keep this x minus 3 that's out in front, that's our linear binomial, and for this we have x plus 4, and we have x minus 4. Keep in mind that x squared minus 16 is a difference of squares. So at this point, this is a linear term, another linear binomial, and another linear binomial. So we can't factor any more than this. This right here is fully factored. Let's try another one where we have to factor by grouping. For example 7, let's factor x cubed plus 7x squared minus 9x minus 63. So just like earlier, let's see if we can maybe group these into two different groupings. So the first two and then the second two. So let's go ahead and see if we can do that. So if you want to try and pause it and do it on your own, great. But otherwise, just let it play and let's do it together. So let's have x cubed plus 7x squared. That'll be the first grouping. And then we're going to have minus. And let's start the second grouping here. Inside here, we'll keep this 9x because it's a negative 9x. But because we need to have a minus 63, what we're going to do is we're actually going to write plus 63 inside of this grouping. Okay, so just to show you that one more time, this is a minus 9x that we had before. So if we take this negative and we distribute here, that would be a negative x. But we have a negative 63 over in the original problem. So we need to make this positive because if you multiply a negative times a positive, it's going to be negative. So that's why. Now that we have our groupings, in the first grouping, what we see is a GCF of x squared. That's what I see. And we factor out x squared, and we're going to be left with x plus 7 left inside the parentheses. Those have no more common factors. And then in the next set of parentheses, it looks like they both have 9. So I'm going to factor out 9 outside here. And factoring out a 9, we should be left with x and then plus 7. Okay, so we just did some factoring for each of those groupings. And what you're going to notice here is that both of these are going to have some common parts. So if we look at these as a whole, right, if we look at this as one term since it's being multiplied together and this as another term, we can notice that they both of these terms have this x plus 7 that's in common, right? So we can factor that out. And if they weren't the same, then we just can't factor by grouping. But since they are, then in this case we can. So x plus 7 is what they had in common. And what they didn't have in common was this x squared minus 9. All right, so what we have in front here, this x plus 7, this can't be factored anymore, right? That is done. However, looking inside here, pause the video and maybe think about this if this looks familiar, this type of pattern. And if you notice that it's a difference of squares, that's fantastic. So in front, we're going to leave this x plus 7 alone. That can't be factored anymore. It's linear. And this x squared plus 9, that should factor into x plus 3 and x minus 3. Doesn't matter which one comes first. They're both good. So this right here is fully factored because all of these are linear binomials, and that's going to be it. This right here is fully factored. Let's try some more different examples now. For example 8, let's try factoring this 16x to the 4th power minus 81. So right away, notice these values are pretty specific, right? 16 is a perfect square, the exponent of 4 is a perfect square, or it's even, and 81 is a perfect square. So maybe we can go ahead and rewrite this into something smaller. So 4x to the 2nd power if we were to square that, right, that would equal 16x to the fourth power. So that's one way to think about it. And then for 81, 81 is really the same thing as 9 to the second power. So if we write 9 squared, that would be also going to be the same thing as 81. So if you look at these two pieces here, this 4x to the second power, raising that to the second power, and raising 9 to the second power, hopefully this makes sense that this is a difference of squares. Again, you can look at these exponents here. So this is a perfect square minus another perfect square. All right, so if we were to go ahead and do that, this is just a difference of squares pattern. So we could rewrite this as the quantity of 4x squared plus 9 multiplied by the quantity of 4x squared minus 9. All right, so this right here would be the first factored form of this original polynomial, but I think there's something more that we can do. So if you want to pause and think about it, go ahead and do so. Otherwise, let me see if I can show you what that's going to be. All right, so if you look at this first binomial, this is 4x squared plus 9. This is what we call a sum of squares, right? 4x squared is a perfect square and 9 is a perfect square, but there's no such pattern as a sum of squares that we're talking about here, okay? You can't factor this. However, if you were to take a look at this binomial of 4x squared minus 9, what's interesting with this is that this is another difference of squares, okay? So in the front, we're gonna have this 4x squared plus 9. That can't be factored. We just finished talking about that. However, this 4x squared minus 9, I could rewrite it as squares again, so I'll go ahead and do so. Inside here, this is really going to be 2x, that's going to be squared, minus a 3 that is squared, right? So you can see here that we do have our perfect squares again. So 2x to the second power is equal to 4x squared, and then 3 to the second power is equal to 9. So fully factoring this out, we can say this is going to be 4x squared plus 9. That was a quadratic, but it's not factorable. And this is going to factor into the sum of 2x plus 3 multiplied by the difference of 2x minus 3. All right, so this right here in the beginning, this is a quadratic, but it's not. So this right here in the beginning is a quadratic, but it's not factorable. This is linear, which is not factorable, and this is also linear, which is not factorable. This right here is the fully factored version for this polynomial. Let's try another. For example 9, let's go ahead and try factoring 2c to the 8th power plus 10c to the 5th power plus 12c to the 2nd power. So right away, I notice that all three terms have an even coefficient, so I'm going to factor out a 2, and they both have 2 of these c's multiplying together, so I'm going to factor that out as well. And if we factor that out, we're left with c to the 6th power plus 5c to the 3rd power, and then we're going to write plus 6 at the very end. So out in front, we have this 2c to the 2nd power that is a monomial, can't be factored. And on the inside here, this one actually can be factored. All right, so keep in mind that c to the 6th power is a perfect square. So if you weren't sure about that, c to the 6th power, anything to an even exponent is a perfect square because it's really c to the 3rd power times c to the 3rd power, also known as c to the 3rd power squared. So keep that in mind, and that might help you kind of notice if you have an even exponent that it is a perfect square. So we can actually factor this into two binomials, but maybe we can see here what two values can multiply to get to 6 but add to get to 5. I'm thinking maybe we can do c to the 3rd power and c to the 3rd power. And if we do a positive 2 and a positive 3 here, let's see if we link those up. That would be 2c squared plus 3c squared. That would be 5c squared total. And 2 plus 3, or 2 times 3 rather, does equal 6. So inside these parentheses, we can write c to the 3rd power plus 2. And then we can write c to the 3rd power plus 3. Okay, so this right here would be a factored version of what we just had above, even though we had higher degrees. Notice what's really kind of interesting here is that this 6 is double of that 3, and that's a big indicator that you can still factor. At this point, this monomial is not factorable. This is also not going to be factorable, even though it's cubic. There is no way to factor this. And over here, this is also cubic, but we cannot factor this either. So we are all done. This right here is fully factored. For number 10, let's see if we can factor 16e to the 4th power minus 625. Right away, if you want to pause it and see if you can try it on your own, or pause to see if you notice a pattern, go ahead and do so. Otherwise, I'm going to go right ahead through it. So looking at this from the beginning, I see this minus sign. I'm automatically thinking of difference of squares. So the only thing you might need to ask yourself is 16e to the fourth power a perfect square? I would say yes. And for 625, is that a perfect square? If you're not sure, check it on a calculator, but I know the square root is 25. So this is indeed a perfect square for both of them, so it's going to be a difference of squares. So factoring this, I can write the square root of each one, so it's going to be 4e to the second power plus the square root of 625, and take the square root of 16e to the fourth power, which is 4e to the second power, and take away 25. All right, so what we have in the beginning here, this is actually going to be a sum of squares, but there is no pattern of sum of squares that's factorable, so we don't have to worry about that one. But take a look at this one here, and maybe pause to think about it. Do you notice anything about this particular part of it, right? So if you think you'd see it, great. Otherwise, this is another difference of squares, right? So I'm going to go ahead and just copy down this 4e to the second power plus 25 in the beginning. And then what we have over here is the square root is going to be 2e, and then we're going to write plus 5, and we're going to have 2e minus 5. So this was kind of like a difference of squares hidden inside of a difference of squares, so that's kind of neat. And at this point, this is not factorable. You can try, but I promise it's not. This is linear, which can't be factored, and this is also linear, which can't be factored. This right here is fully factored. For number 11, let's try factoring 4f to the sixth power minus 20f to the fourth power plus 24f to the second power. Right away, looking at this polynomial, I notice that 4 is a common factor for all three terms. They also all have f to the second power, or 2f's. So factoring that out, we should have f to the fourth power, and then minus 5f to the second power, and then plus 6. All right, so that would be what we have left inside after factoring out the GCF. This monomial here can't be factored. However, inside here, this is a trinomial, so we might think that we could factor this possibly, and I think we can. So I mentioned a little bit earlier, when you notice that this exponent here is even, then it's a perfect square, and if it's double of this, then we might be able to factor into two binomials, even though the degrees are higher. So it turns out this trinomial is factorable because f squared times f squared does equal f to the fourth, and negative 3 times negative 2 multiplies to get positive 6, and they add to get to negative 5. So that's negative 3f squared, negative 2f squared, that's negative 5f squared combined. So this is factorable. So out in front we have 4f squared, and we could factor this into f squared minus 3 multiplied by the quantity of f squared minus 2. This monomial can't be factored. This is a quadratic, but it can't be factored, and this is another quadratic that can't be factored. There we go. So at this point, we've completed 11 practice problems together, and I hope you feel a little bit more comfortable with using some of these strategies and noticing these patterns. And if you want to stay tuned for a future video, I'll go through a bunch more practice problems, maybe a little less explanation, but just going through some practice problems that we can try together. So hopefully this was helpful. If it was, give the video a thumbs up and consider subscribing if you're really helpful for this channel. And as always, keep up the great work, and I'll see you in the next one.